Okay, we had a question in our homework this week that many of you struggled with on this particular problem. This is in chapter 13-2, and we're given a couple figures, triangle XYZ and triangle X prime, Z prime, Y prime, and we're asked to transform this one onto this one by a series of successive reflections. Now, right away, it should be pretty apparent that this is not a reflection itself. The reason being that z and z prime, if we perpendicularly bisected that segment right there, then y would go someplace like here, and x would go someplace like here, and it doesn't look like that's going to work. So certainly isn't a pure reflection. But the fact that orientation has been reversed, x to y to z is clockwise here, x to y to z is counterclockwise here, means that a reflection was involved. So the obvious implication here is if there was a reflection involved that reversed orientation, but it's not a pure reflection, then this must be a glide reflection of some sort. But the problem statement actually asks us to transform one onto the other by a series of successive reflections. So I'm going to go ahead and show you what I did to solve this problem. Certainly not the only way you could do it, but let me go ahead and show you how I solved the problem. My first goal, or sub-goal, I guess, in solving the problem was to reflect z onto itself here. So what I did is I drew in this segment, and I found the perpendicular bisector of that segment, and I reflected in that particular line. So I went ahead and reflected in the perpendicular bisector of z prime. What that does is take z to z prime, it takes x then to x1 here, and it takes y to y1 here. Okay, so I had one of the vertices of the triangle then fixed, and I want to keep that fixed. I don't want to move it. So my next reflection needs to go through that particular point, or fix that point. And my next goal, or my next sub-goal, I guess, in the problem was to take y, what I'm calling y1, and see if I could reflect it so that it lands on y prime. So in order to do that, what I did is I used this particular angle, and I found its angle bisector, and I thought to myself, well, if I reflect in that line, then it will take this point to that point, because the angle, I guess, here to here will be reflected here to here. So that's what I did. I found the angle bisector of y1, z, y prime, that's this line L2, and I went ahead and I reflected the triangle that I have highlighted onto the new triangle then that's right here, which is, of course, z, I guess we'll call it z2 now, y2, x2. It's the one that's not highlighted in this overlay. And then it's quite easy then to see what we need to do to get x2 to then correspond to x prime itself. We would reflect across this particular line, the line that's defined by z and y prime. The reason we want to do that is because we already have those 2 points sort of located or fixed, and we want to fix them again. And of course, that will take this point to that point, because the perpendicular bisector will be located there on the line of reflection will perpendicularly bisect the segment that connects x prime to x2. So that's the way I solved it, 3 successive reflections to go ahead and get that original triangle to match up to the image down here. One thing that should make sense to you is that each time I reflect, I reverse orientation. So original, reversed orientation here, reversed orientation to the middle one. So this one's orientation, this sort of x2, y2, z. This one has the same orientation as above, so we need to reverse one more time to get to here. So an odd number of reflections will indeed yield a reversal of orientation, whereas an even number of reflections would have maintained orientation. So it seems to make sense that you would need an odd number of reflective lines to get from the original to the transformed triangle down below.